In this video, I want to talk about systems of equations and talk about some of the vocabulary and some of the lingo and how we can write our solutions. First off, lingo. A solution to a system of equations is an n-tuple that makes each equation true. Now, what I mean by n-tuple is if we're in 3 space, it will be a 3-tuple. If we're in 2 space, it will be a 2-tuple. If we are in R20, it will be a 20-tuple. A consistent system of equations means it has at least one solution. So homogeneous or homogeneous systems of equations are always consistent. They always have at least the 0-tuple or the 0 vector. If there's no solution, we call it an inconsistent system of equations. So let's look at some examples. I have 2 equations, x plus y equals 3, x minus y equals -1. I have 2 variables, so we can assume that we are in R2. These are 1 dimension less, so there are equations for lines. 2 lines can meet in a couple different ways. They can be parallel, they can cross at one point, or they can actually be the same line. This one we have here, x plus y equals 3, x minus y equals -1. The augmented matrix looks like that. And when I put it in reduced row echelon form, I get this 1, 0, 1, 0, 1, 2. Reading from that, I can see that x equals 1 and y equals 2. So these 2 lines meet at a point. Check out this example. We have x plus y equals 3, 2x plus 2y equals 6. Matrix for this is 1, 1, 3, 2, 2, 6. Second row is a multiple of the second one. That should be a giveaway that it is the same line. When I put it in reduced row echelon form, the second row is gone. All I have is a top row, which is the same as the first equation. So these 2 lines are the same line. Lastly, let's look at, I just did it all at once. Lastly, let's look at x plus y equals 3 or x plus y equals 1. Now you should look at that and you go, well, it can't be 3 and 1. We're going to have something weird here. So if I put it in row reduced echelon form and put it back in the equations, the first equation is x plus y equals 0, and the last one is 0 equals 1. 0 never equals 1. There's no solution. This is an inconsistent system. They're parallel lines. So let's get something a little more complicated. Here we are in R3 because I have 3 variables, 3 equations. So each of these equations represents a plane. Do they intersect? Well, first I want to think about the matrix. But before that, I want to make sure I put zeros in the variables that are missing so I don't screw up my matrix. It can be written this way, or these equations can be written this way. Notice I have this matrix of coefficients, that's why it's called the coefficient matrix, times this vector, x, y, z, and it has to equal this other vector, 9, 5, 2. If I did the multiplication out, I would get these systems of equations every. Furthermore, I can simplify this, not simplify it, write it more concisely. I can write this as ax equals b, where x is a vector, b is a vector, and a is that coefficient matrix. So let's find the solution to this thing. There is my matrix. I have the line there just to remind myself that that's where the equals are. You don't have to do that. If I put it in row reduced echelon form, I get this matrix. And then putting that back in that matrix form that I have my coefficient matrix now is this, which is, by the way, the identity matrix, times x, y, z equals 1, -1, 2. If I were to multiply that out, I would get x, y, z on the left and 1, -1, 2 on the right. So my solution is 1, -1, 2. Another gross one. We're getting so many variables, I'm starting to use numbers. So this is x sub 1, negative x sub 1, 2 times x sub 4, etc. I'm not going to read out all of those equations. That would be my coefficient matrix. And this, I don't think I put the line here. No, I didn't. So my line of 0, my equal sign goes before that last column. If I put this in reduced row echelon form, I get this, which now I'm going to remind myself that's an equals. So all of my variables are equal to 1. So x1 equals 1, x2 equals 1, etc. Everybody equals 1. Another example. Okay, now I'm in 3 space and I have 2 planes. So I know I'm not going to get the solution of just a point. I know I'm going to get a solution because it goes through 0, 0. These are homogeneous equations. This is my coefficient matrix or my augmented matrix. Reminding myself what the zero is, I put it in reduced row echelon form, and I get, oh my gosh, I'm so glad I have maple. So I have 1, 0, 19, 20 seconds, 0, 1, negative 1 over 22. Now, since my 0 is here, my equal sign is here, I don't have x equals this and y equals that. This is my z column. X and y are where the pivots are, so they are dependent variables. And z didn't have a pivot. It's pivotless. So it is an independent variable. That means z can be anything. Z is any real number. And x and y are written in terms of z. Remember, this is where the equal sign is. So this would be x plus 19 20 seconds, z equals 0. If I solve for x, I will get this. That's why the signs are changing here. So that's the solution, but it's not a really good way of writing it. It's kind of shitty. So let's see if we can do better here. I have my solution, and in terms of a vector, we usually write x, y, z. So x is negative 19 20 seconds z, y is 1 22nd z, and z is z. So I can factor z out of all of these. And I'm not really liking all those fractions because I do not like fractions. And since z can be any real number, if I factor out 1 22nd times z, that's still going to be anything times a number is still anything. I think of it as multiplying it through or pulling it out. Anyway, I'm just going to get rid of the 22. So I have to suck out a 22, which means that last one was multiplied by 22. So my solution is z being any real number times the vector negative 19, 1, and 22. Now we can do better. I know we can. So basically I'm saying any multiple of that vector, which in other words, if you've watched the other video, which I sure hope you have, it's the span of that vector. So when I say the span, it means any multiple of that vector. Let's go and do another gross one. That's not too gross. I have 4 variables. I'm in R4 with 2 equations, which means my solution should be 2-dimensional. So let's see what we get. I have my coefficient matrix there. Put it in row reduced. Oh God, thank God for maple. I have some really gross fractions here. Notice that x and y have pivots. Z and w don't. So x and y are dependent and z and w are independent. Z and w can be any real number, but x and y are going to be written in terms of z and w. So let's write this as a vector. The vector is, this is my x expression, here's my y expression, here's z, here's w. I want to clean this up. Boy, do I want to clean this up. This sucks. I can split these up into the z's and the w's. So here are all my z's and here are all my w's. I just unadded these 2 vectors. So this first one, I can suck out all the z's, and the second one, I can suck out all the w's. So I have this. And again, fractions suck. So I want to pull out a 1/42 over here and pull out a 1/14 here. So I get z times that first vector plus w times that second vector. So the solution is going to be any linear combination of these 2 vectors. In other words, it's the span of those 2 vectors. And we also call this the linear combination of 2 vectors. That's how we're going to want to start writing our solutions if we can. When it's non-homogeneous, you end up with this kind of crappy extra vector sitting out front, but that's okay. We could do that too. But the solutions we're going to want to talk about are in terms of the span of these 2 vectors. And these 2 vectors will be the basis of the solution space, which should make sense if you've watched the other video. And I think that's a really good place to stop because it's late on a Friday and I want to go home.